This video will continue the series of videos on acid-base chemistry with discussing buffered solutions. So buffers are solutions that contain a weak conjugate acid base pair. So some of these could include, HF and F minus, HC2, H3O2, so acetic acid and acetate. Phosphoric acid and then the conjugate base, H2PO4 minus. Any weak acid, weak base pair that you have is a buffer if you have concentrations of both of them. And what buffers do is they resist large changes in pH upon addition of strong acids or strong bases. Right, this is why your blood is able to maintain a pH right around 7.4 or so, because it has a buffer of conjugate acids and conjugate bases. And your blood has a complex buffer. It's made up of more than just one pair of compounds, but it's able to maintain a pH close to what your body needs. Right? That's why you don't drink a glass of lemonade and your blood pH drastically changes. That doesn't happen because of the buffer capacity of the blood. Now, depending on the conjugate acid-base pair you choose, you can buffer a solution at virtually any pH. We'll go into why a buffer's pH is related to the pKa of the weak acid in that buffer. So we'll talk about that by using the Henderson-Hasselbeck equation. So Henderson-Hasselbeck. This is the most important equation for buffers. In this equation, states that the pH is equal to the pKa plus the log of the concentration of your conjugate base over the conjugate acid. When the concentration of the conjugate base is equal to that of the conjugate acid, this cancels out and your pH is equal to your pKa. So by choosing a buffer in which the conjugate acid has, say a pKa of 4.7, you can have a pH of right around 4.7 if you have similar concentrations of conjugate base and conjugate acid. And you'll see that more when we run through some examples of how to calculate the pH of a buffered solution. So first example here. So what is the pH of a buffer that is 0.12 molar in acetic acid and 0.10 molar in acetate? And the Ka of acetic acid is 1.8 times 10 to the minus fifth. So I'm going to start off by writing out the equation of the reaction that's taking place here. So we have acetic acid plus water is in equilibrium with acetate and hydronium. Like any equilibrium, I'll set up the ice table. Right, I'm going to show both ways of how you could solve this. So the first one, I'm going to do what we always do with the ice tables in terms of equilibrium problems. So I have my initial amount of acetic acid. I know it's 0.12 molar. Initially, I have 0.10 molar acetate and no hydronium ion. The left side is going to be minus x, while the right side is plus x, because for acetate to react with hydronium to form acetic acid, I need to have hydronium, and I don't have any hydronium to start. So the reaction's gonna proceed to the right so that I can form the hydronium. So then at equilibrium, I have 0.12 minus x, 0.10 plus x, and x. Now, I'm going to say Ka is equal to the concentration of hydronium, so that would be x, times the concentration of acetate, 0.10 plus x, over the concentration of acetic acids, 0.12 minus x. Given the Ka is pretty small, times 10 to the minus fifth, and we have 0.1 molar and 0.12 molar, I'm going to approximate that that x is so small that it doesn't really change 0.10, 0.12. And by doing that, I can cross out the plus x and the minus x parts, which makes this calculation much easier. So once I do that, the concentration of x is equal to Ka times 0.12 over 0.10. So Ka is 1.8 times 10 to the minus fifth times 0.12 over 0.10, and that is going to give me 4.67. Oops, that's not my answer quite yet. Sorry, that doesn't give me 4.67. This gives me 2.16 times 10 to the minus fifth. I'm a little bit ahead of myself there. So 2.16 times 10 to the minus fifth molar H plus. So the pH is going to be equal to the negative log of 2.16 times 10 to the minus fifth, and that is 4.67. So that is the pH. And that's solving it using the ice table. Now I mentioned last slide Henderson-Hasselbeck equation. I'll do this in a different color. So the pH is going to be equal to the pKa. So pKa, remember, is just negative log of the Ka. So it'd be negative log of 1.8 times 10 to the minus fifth plus the log of A minus, so acetate, so 0.10 over HA, 0.12. When I do that calculation, I get 4.67. So I get the same answer both ways, but it was much quicker to use the Henderson-Hasselbeck equation. But I also wanted to show you that we get the same thing if you use the ice table. So if you're very comfortable with ice tables and don't want to have to worry about memorizing another equation, you can certainly use the ice table and get to the same answer. So now I'm going to discuss a couple of terms that are important with buffers. The first one is going to be buffer capacity. And this refers to the amount of acid or base that a buffer can neutralize before an appreciable change in pH. So the greater the concentration of conjugate acid base pair, the greater the buffer capacity. Right, and that seems to make sense. If I have a buffer of 1 molar acetic acid and acetate versus a buffer of 0.1 molar acetic acid and acetate, the buffer with 1 molar of each of them can accept more acid or base before there's an appreciable change in pH, just because there's more buffer present. Now the second one I want to go over is the pH range. So this is going to be the range of pH in which the buffer is effective. And generally, a buffer is effective in a pH range that equals the pKa of the acid plus or minus 1. So acetic acid, for example, Ka is equal to 1.8 times 10 to the minus 5th. That means its pKa is just the negative log of that, and the negative log of 1.8 times 10 to the minus 5th is 4.74. So that means a buffer of acetic acid and acetate would have a pH range from 3.74 to 5.74. So in that range, it would work well as a buffer. And it would work best as a buffer right at a pH of 4.74. All right, last thing I want to discuss with buffers is that when a strong acid or a strong base reacts with a buffer, the reaction proceeds to completion. So in this example, I have a buffer with 0.400 moles of HF and 0.400 moles of F minus. It has a pH equal to 3.10. And this is all in 1 liter of water, or 1 liter of solution total. So first thing, we have an equal amount of HF and F minus, meaning our pH is equal to the pKa. Remember I showed before, so pH is equal to pKa plus the log of here, it's going to be F minus over HF. Those are the same, so our pH is equal to our pKa. So what is the pH after the addition of 10 milliliters of 1 molar NaOH? So the NaOH is reacting with the HF, right? That's the acid-base reaction, and it proceeds to completion. So first thing I'm going to do is just, if I have 1.0 moles per liter of OH minus, 10 milliliters is 0.010 liters. This gives me 0.010 moles of minus OH. So if I set up an ice table now of the reaction, HF plus NaOH right, that's in equilibrium with F minus plus H2O. Let me just put down here, everything's aqueous except for the water. So set up the ice table. I'm going to just put in the moles here. I'm not going to put in the concentration because we don't need to do that. Right? Everything is in the same volume of solution, so we can use just the moles. So we have 0.400 moles of each of those. Initially, no NaOH. Now we add in 0.010 moles of NaOH. And when we do that, since it proceeds to completion in its reaction with HF, we lose 0.10 moles of HF and we gain 0.10 moles of F minus. We ultimately have 0 NaOH left at the end, since it reacts completely with the hydrofluoric acid. So then at equilibrium, or the reestablished equilibrium, 0.39 moles of HF and 0.41 moles of F minus. So then the pH is going to be equal to the pKa, which is 3.10, plus the log of F minus 0.410 over HF 0.390. And this gives 3.12. So we hardly had any change in pH. We had 0.02 change in pH units when we added in 10 milliliters of 1 molar NaOH. If we had added that just to pure water, the pH change would have been drastic, but it hardly changed at all because we were using a buffer. So in my next video on acid-base chemistry, I'll go into titrations.